So let's review for part one of today's. And what we're going to do is just make a table up and review our notations that we use for an isotope. And what we're going to do for each of these isotopes that we list, we're going to record the number of protons, and I'm just going to use a P for protons, the number of electrons, and we'll use a lowercase e for an electron, and the number of neutrons, we'll use an N. And we're going to put a line, and we're going to discuss 3 different isotopes. So you may have done this already, but let's just go through each of these. Let's look at our first guy right here. Now, this isotope, we would refer to this as carbon-12. Normally, when we say it's an isotope of carbon-12, number that we're focusing on is this larger number. And as you recall, the larger number, the number that sits in the upper left-hand corner, that's called the mass number. And remember, the mass number is the number of protons and neutrons in that nucleus. Okay, so let's think about the number of protons in this particular isotope. The protons are listed according to the atomic number. And the atomic number is the number, I'll put a square around, that's listed in the lower left-hand corner. For carbon-12, the number of protons are 6. And as you recall, we talked about in our last lecture, the number of protons is what's unique for a particular atom. Every atom of carbon has 6 protons in its nucleus. Next part of our table, how many electrons are we going to have for carbon-12? Well, these are all neutral isotopes. They don't have a charge on them. Since they're neutral, and if you recall, protons are positively charged species, electrons are negatively charged, and neutrons are neutral, they have no charge, then the number of electrons have to be equal to the number of protons. So for carbon-12 in this example, there has to be the same number of electrons as protons, since this is a neutral isotope, a neutral atom. How many neutrons do we have? Well, the number of neutrons, remember our definition of the mass number, it's the number of protons plus the number of neutrons. The number of neutrons is equal to the mass number, 12, minus the atomic number, the number of protons, 6. So that's what we get for our carbon-12 atom. 6 protons, 6 electrons, 6 neutrons. Let's move to our next isotope. This is an isotope of Fe. Fe is iron. Now, remember, when we want to determine the number of protons are equal to the atomic number, 26. It's a neutral atom. There has to be the same number of electrons as protons, and that is also 26. The number of neutrons, that's going to be equal to the mass number, the mass number is 55, minus the atomic number, 26. And that tells us that this particular isotope has 29 neutrons. Good so far? Let's do our last one. Our last one, that's potassium. Potassium has a periodic symbol K. Once again, the number of protons, 19. It's a neutral atom, needs to have 19 electrons. The number of neutrons is the mass number, 39, minus the atomic number, 19, which is the number of protons. This isotope of potassium has 20 neutrons. So that goes over how we can use isotope notation to list the number of subatomic particles in a series of isotopes that we are given in this example. We also discussed there are sometimes shorthand ways of writing our isotope notation. And I wanted to show you one as an example. Mg24. This is what we call an isotope of magnesium, and it would be called magnesium 24. Now, it doesn't give us a lot of information. All it tells us is the mass number. This notation requires us to use our periodic table a little bit. And I have one on today's PowerPoint. You would look at your periodic table. And on your periodic table, you would find Mg, which is magnesium, and there's a whole number on it, 12. Well, that's its atomic number. That's the number of protons in the nucleus of any magnesium atom. So let's do our table here, and let's write down the number of protons, electrons, and neutrons. Protons is equal to 12. That's the atomic number that we find on the periodic table. Number of electrons is going to be the same since it's a neutral atom. And the number of neutrons, that's the mass number, 24, minus the number of protons. And in this case, it has the same number of neutrons as protons. So you should recognize that we don't always have the same number of protons and neutrons. Sometimes we have different numbers of them. And that's a feature that you'd learn more about in nuclear chemistry to understand a little bit about why some isotopes are quite active and why they form. Let's do one more example. Another shorthand notation. The one I discussed a little bit about at the end of our lecture. Sometimes we see an element symbol listed with a whole number, or you might see this as bromine 79. This number that we list with it is the mass number. And remember what we said, the mass number is equal to the number of protons in that nucleus plus the number of neutrons. So this question that I asked in this review section, how many neutrons does this nucleus have? In other words, how many neutrons are in the nucleus of bromine 79? Well, again, we would need to use the periodic table. If we looked at the periodic table, we would see that there's a whole number, 35, listed on bromine in the periodic table. Well, that's the number of protons. The mass number is listed here. So the number of neutrons, 79 minus 35, and that's 44. So that's another example of how we can use a shorthand notation to represent the number of subatomic particles, or if we ask you about one specific subatomic particle, such as the number of neutrons, then you should be able to answer that question. So, conceptual question. Isotopes. What do they have different numbers of? Well, they have different numbers of neutrons, and therefore they're going to have different mass numbers. Again, remember we discussed a little bit on the other lecture. Carbon, we can have carbon 12, there's carbon 13, and there's even carbon 14. Hydrogen, we have hydrogen as known as protium, which is hydrogen 1, hydrogen deuterium, which is hydrogen 2, and hydrogen with a mass number of 3, which was tritium. So, as we said, there are differences between another type of particle that we might be should become familiar with, and that's ions. So let's discuss what ions are and understand a little bit about them. Ions, as we mentioned at the beginning of today's lecture video, these are charged particles. So they're charged particles. And when we say they're charged particles, the reason why they're charged particles is because they're either going to have an excess number of protons, in which they'll be positively charged particles, or they're going to have an excess number of electrons, which means they're negatively charged particles. Now, what normally is going to happen is these atoms are undergoing what we call oxidation and reduction reactions. In some cases, there's a complete loss or gain of electrons, and in other cases, there's going to be a partial exchange of the electron. But it's the gaining or losing of electrons which results in this charged particle. No gaining or losing of protons. It's the exchange of electrons which gives us these charged particles. Now, we need to define two types of charged particles. The positively charged particles are called cations. These are positively charged. And notice I underlined my T because that's how, when I was an undergrad, I memorized it. It was just like cations have this T in the middle, and that just caught my eye, and I'm like, cations are positive. So if that helps you, great. Anything that helps you learn is the best of, it's good. It's going to help you. Okay, they're positively charged particles due to the loss of electrons. So when a particle loses electrons, they're going to have an excess number of protons in their nucleus, and that particle is going to be charged. So these are due to the loss of electrons. Let's consider an example here, and we're going to learn more about how we can predict the charge of what we would expect an atom to form when it undergoes an oxidation and reduction reaction by assigning what we call oxidation numbers. And we're going to be able to make these predictions based upon the atom's position in the periodic table. We'll learn about the rules a little bit later, but what we want to look at beryllium, an atom of beryllium. Beryllium. If we look at beryllium and recognize where beryllium is in the periodic table, beryllium in its atomic form, if you look on the periodic table, that's what you're going to see for beryllium. There's a 4 on it. Beryllium, neutral atomic beryllium. It has 4 protons and 4 electrons. That's all we know about this atom right now. We don't give you any more information. We're not giving you its mass number. All we know for sure is based upon its position in the periodic table. What we know is that an atom of beryllium has 4 protons and 4 electrons. Okay? What beryllium may undergo a loss of electrons. And this is typical for atoms that sit in the periodic table where beryllium does. And again, we'll learn more about this a little bit later. Beryllium might lose 2 electrons. So let's just make sure we remember these are positively charged. These are negatively charged. And when we have equal numbers of positive charge and negative charge particles, beryllium is a neutral atom. What happens if this beryllium atom, we're going to put a minus sign, just like we're subtracting. We're going to remove 2 electrons from the beryllium's surrounding the nucleus. And we're going to end up with what we call the beryllium cation. And we normally write these with a little superscripted positive 1 for the cation. And since it's lost 2 electrons, beryllium has 2 additional protons in comparison to the number of electrons. And therefore, the beryllium cation has 4 protons, 4 units of positive charge, and it lost 2 of its electrons, 2 units of negative charge, and now we have an excess amount of positive charge, and we have what we call the beryllium cation. And as we said, beryllium cation has a positive 2 charge because they have additional number of protons in comparison to the number of electrons that surround their nucleus. And that's how we define a cation. Cations are caused by atoms that lose electrons, and they're positively charged. Let's look at the other case. Since we have positively charged particles, we also have atoms that can gain additional electrons. Atoms that gain more electrons than protons that are in their nucleus are called anions. I'm going to underline my N, anions. I underline my N. Again, it sits in the middle of this. And this is how I remembered it. These are negatively charged particles. Anions form by gaining electrons. There's no changing of the number of protons. The number of protons remain constant. The only thing that's changing is the number of electrons that surround the nucleus in a particular atom. Let's look at an example of chlorine. Chlorine is an atom that typically forms an anion that has a -1 charge. Chlorine. Let's look at chlorine based upon its neutral state. If we look at chlorine, chlorine has 17 on it. Okay. And what that 17 tells us is that chlorine in its neutral atomic form, protons, remember, are positive charge. It has 17 protons, and it has 17 electrons, which are negatively charged species. Since we have an equal number of positive charged species and negatively charged species particles, we have an atom that's neutral. Chlorine And again, we'll learn more about where it's positioned at in the periodic table and how we can make predictions a little bit later. An atom such as chlorine gains an electron. So let's add an electron. We're going to add one electron. We're going to add one more electron to its nucleus. And we're going to put a negative symbol on there. We don't need to write 1. If you do write a 1, I'm not going to have a heart attack. That's fine. But normally, if it's only 1, we just leave that as a negative. And let's think about what's happening in the nucleus now. The number of protons do not change. Still got 17 of them. We've added one additional electron. We now have 18 negatively charged particles that surround the chlorine's nucleus. We end up with a negatively charged anion, and we'll call this the chloride anion. We'll learn more about terminology. This is called the chloride anion. And anions form due to the gaining of electrons. And remember, the key feature of ion formation is gaining or losing of electrons, not protons. Make sure you understand that. That's very important. The number of protons remain constant. The atom's identity does not change. The only thing that changes is the charge on the new particle that's formed. And that's really important as we move a little bit later in this course and discuss oxidation and reduction chemistry at the end of this course. And we'll learn more about that a little bit later. So just to briefly review what we discussed today. We discussed isotopes and went over isotope notation, and we showed how they're different than ions. So let's answer a question. Question A, true or false? Different isotopes of the same element have different mass numbers. True or false? Think about it. Stop the video. That's true. They're going to have different mass numbers. That's because they have different numbers of neutrons. Mass number is protons plus neutrons. Since the neutrons are different, mass number is going to be different. Let's think about another question. This is a good one. Let's write this one down. True or false? So we can see this as an exam question. True or false? So let's think sodium, Na is sodium, and Na positive. That's the sodium cation that was formed by the loss of an electron. These two, do they have different mass? We'll just say have different mass numbers. Sodium and sodium cation have different mass numbers. Different atomic mass numbers. How's that sound? True or false? They have different atomic mass numbers. Stop the video. You can think about it. That would be false. That'd be false. That's false. The reason is they have the same number of protons, and without additional information, we don't know how many neutrons. So without that additional information, we would have to say that that statement is false. So cations and the formation of an ion from a particular element doesn't necessarily mean that these two species are going to have different mass numbers. So that's the end of our first part of our lecture. We're going to finish chapter 1 in the second half of our lecture by introducing what we call the atomic mass unit, and we're going to discuss a little bit about the mole concept. Thanks a lot, and we'll see you in part 2.